Okay, so it is 2:01. So let me start today's lecture. I guess up to the previous class, we had talked about the vacuum distillation column. Like, why do I need to use vacuum distillation column? What are the products that we are getting out of vacuum distillation column? So, but we also talked a little bit about, like, for example, different fractions that are coming out of vacuum distillation. It may not have always the same type of boiling point range. So the boiling point range will vary between some initial boiling point to some final boiling point range. So for example, for vacuum gas oil, it varies between 237 to 368 degrees centigrade. For spindle oil, it varies between 339 to 426. Similarly, for light oil, between 390 to 485. For inter oil, between 540 to 578. And for heavy oil, it varies between 485 to 608 degree centigrade. But the one thing we hello.
Sir, your voice is a little, it's breaking a little.
Hello, just a minute. Okay. Just a minute. Just a moment. My voice is breaking.
Actually, now it's clear, sir.
Now it's clear, right? Okay. So let me just further continue on this. So like let's see that here that I have talked about, that different types of petroleum fraction that are coming out of vacuum distillation unit. If you do this distillation at atmospheric pressure, you see we have to heat up all of this petroleum fraction at a very high temperature. So I have told you that whenever we are dealing with petroleum fraction at a very high temperature, then there is a chance that it may thermally degrade. You won't be able to produce too much of a valuable petroleum product. So that is what also needs you need to look at. So you can see that in spite of the range that I have reported here, these are all are reported in terms of atmospheric pressure. But actually, when this vacuum distillation column operates, you see the spindle oil is coming around to 13 degrees centigrade. Your uh, light cycle oil coming around your like 263. Your inter oil between 325. Your heavy oil between 360, and your slope oil between your 381. And you see that your vacuum distillation, like from your vacuum distillation feedstock itself, is entering the system at 405 degrees centigrade. So pretty much you have to understand all of this boiling point can only be achieved, or let's say such separation can only be achieved at a lower pressure. So our normal atmospheric pressure is approximately 760 mmHg, and you can see at the top of this column it is operating at, let's say, at 20 mmHg. So where you are getting the some of the top products. And then if you come down, you can see that although the bottom part is actually operating at a little bit higher pressure, but it is also within the limit. You can see that in this part. So the this bottom part is operating at a little bit higher pressure. So it is around for like 40 mmHg, but it is considerably low compared to my atmospheric distillation. So like if somebody tells you that whether let's say in your distillation like vacuum distillation column operates between what pressure range, you would be able to say that between 20 to 40 mmHg. So that pressure range it operates. And I have already talked about all the products at atmospheric pressure, what are the a particular let's say boiling point range we are coming up with. And at vacuum said that spindle oil is extracted at 213. So that those discussions we have already covered it up. So before I move on and discuss about a little bit more on the, let's say, if there is like adverse vapor flow condition between inside our distillation unit, what are the demerits can take place in terms of, let's say, my product quality, my let's say in terms of like whether I'd be able to produce more lighter products also, that is also going to be determined by the vapor flow within the system. So the quality of the product, if there is adverse vapor flow condition, is going to be really poor. So before going towards that side, so for that purpose I have a video to show you people. So just by looking into this video, you should be able to understand how this vapor liquid interaction, or let's say the vapor flow within the distillation column, can affect your product quality. So this information is pretty much required, and 100% questions will be there. Like let's say in cat 1, in final examination, 100% question will come from this vacuum distillation unit. Plus let's say if the vapor flow condition is let's say altered in your distillation column, what is going to be the effect on the product quality. So similar type of question might come in the final examination as well as in the cat 1. So this part is very important and you have to understand it very properly. So let me just go further forward with the slide. So as you can see that this I have already discussed it a little bit earlier also, that based on the crude oil that you are processing, you are definitely going to come up with different type of petroleum fraction. Let's say the type may remain the same, but the quantity that you are going to be able to produce is definitely going to be a little bit here and there. So high sulfur content, like if you have high sulfur content, high density also, there is a more chance that you will come up with more and more residue product. So you see the vacuum residue part using high sulfur crude is going to be more, and for your low sulfur crude it is a little bit on the lower side, but the other naphtha is almost like very close to each other. So let me just move forward to talk a little bit about, because since we are talking too much about atmospheric distillation column, vacuum distillation column, but we also need to understand what are the internal structure, what are the key components of a distillation column. So in order to understand that, so you can see at the right hand side, this is the main components present in your distillation column has been displayed here. The distillation column can be classified into two separate zones. You can call it at the middle point, your feed is entering into the distillation column. Whatever that is above that feed tray, you can call it as enriching or rectification section. And whatever that is below the feed tray, you have to call it as a stripping section. And at the bottom of the your uh, like crude oil distillation column or any distillation column, there has to be a reboiler where the heat is going to be supplied to your particular distillation column for the separations to take place. So reboiler section is present at the bottom, where uh, uh, like you have to extract a little bit of feed from the bottom, then reboiler will heat it up and then it will again inject it, and some of the amount like heat exchange, those things will definitely take place, and bottom product. So if you consider this as a let's say atmospheric distillation column, so the bottom product is going to be RCO, that is reduced crude oil. And you see at the top of the section we have a condenser section, where let's say if the lighter, so the gas products will come out, so it has to be properly condensed. So some of the amount is going to be stored in the reflux drum, where it will be stored, and then again it can send a part of it back into the distillation column for better vapor liquid interaction, because the more vapor liquid like contact you have, the better separation it can produce. So like increasing the your reflux can definitely help you reduce the number of trays that you require for distillation purpose also, that can also be reduced, and one part you can recycle it back. So that recycle part is known as the reflux. The other part that you are extracting, you call it as the distillate part. So that is how this thing is actually operating. So there is like another, so if you want to like reutilize some amount of heat from some waste sources, some, let's say some gas is coming out, you want to utilize that heat in your reboiler, so that arrangements are also there. So in order to, let's say if I want to say that what are the five main components of my distillation column, I would list these five components. So first component is obviously the vertical cell, where the separation of liquid components is done. Then comes the column internal. So the column can be of a packed column where small packings can be there, or else like it can be a tray or plate type. So mostly in distillation column, mostly tray and plate type distillation columns are only used in the industry. So that is the common practice. So column internals like tray plates, which are used to enhance the component separation. So columns and plates, if you have it, so it becomes much more easier to have a proper vapor liquid interaction. And I have said previously also that higher vapor liquid interaction means better separation. So you would be able to properly separate the components. Reboiler is to provide necessary vaporization for the distillation column, which is placed at the bottom. So how it is operating, that I have also told you. Condenser is to cool and condense the vapor leaving from the top of the column. So here you are having this condenser. Reflux drum to hold the condensed vapor from the top of the column, so that liquid can be recycled back to the column. So you can actually store a certain amount of liquid depending on how much reflux you want to send it. So like you have condensed it, you have stored it in the reflux drum, a part of it you can actually send it back to the distillation column to enhance the vapor liquid like interaction, or let's say contact, and the remaining part you can take it out as a distillate. So this is the basically the internal parts of your distillation column. So distillation column can be classified into different types. Binary column means like only two components are separated. Multi-component, where if the feed is containing like more than two components, then you call it as the multi-component distillation. So distillation, what it is doing, it is basically based on your boiling point, it is separating two components. So like if your feed is having two components, then you call it, the distillation that you are doing, you call it as the binary column. If it is like your feed contains more than two components, you call it multi-component. The number of products stream, if you have like multi-product column, so the column like the column has more than two product streams. So obviously if it has a multi-component, that it should have more than like more than two streams. And because the petroleum, the crude oil has a lot of fraction, like it is not a one or two component, it has so many components there. So like distillation that we do for crude oil is obviously a multi-component distillation. You can also call it as the multi-product column also. Like where extra feed exit when it is used to help the separation, like extractive distillation, azeotropic distillation, but you don't like dive too much into it. This is actually a part of your what should I call it, this is actually you study this at in mass transfer. So like azeotropic distillation, where like extra feed appears at the top of the product, while like in extractive distillation your extra feed is going to appear at the bottom of your your distillation column, but you just leave it. So this is basically a very selective part in terms of my mass transfer operation. So you will understand it later. So then based on your what is the internal structure of my distillation column, whether it is having trays or whether it is having packed column. So based on that you can call it as tray column, packed column, so like that. So trays of various designs are used to hold up liquid for better contact between vapor and liquid, and I have told you higher the contact, better the separation. Packed column, the packing is used to enhance vapor liquid contact, but compared So distillation column operating problem. So like this would be discussed. Okay.
And the falling liquid in the column.
Can you hear the voice?
Yes, sir.
Okay.
One aspect of operation that can affect this balance is the system's feed rate. The feed rate is the rate at which feed mixture is pumped to a column. The flow of feed to a column can affect the quantity and quality of overhead product and bottoms product. For that reason, an optimum feed rate is normally determined mathematically based on system equipment and the materials being processed. An optimum feed rate is often determined when a system is designed and may be modified according to the mixture being distilled. However, a range within which the system functions efficiently is usually specified as well. For example, a system may have an optimum feed rate of 100 gallons per minute and an operating range of 80 to 120 gallons per minute. The way the feed rate is kept within the specified range depends on the system. In this system, a flow controller compares the rate of flow in the feed line to a preset value. If the feed rate needs to be adjusted, the controller signals a control valve to open or close. A distillation system functions most efficiently when its feed rate is kept within an established range. When the feed rate is regulated by a flow controller, slight variations in the rate can be expected. However, large variations can greatly affect a column's performance. If a system's feed rate is too high, overloading can occur. Overloading is a condition in which the vapor rising up a column is impeded by the liquid flowing down the column. For example, if the feed rate for this trade column is too high, the liquid will back up in the downcomers and build up on the trays. The increase in hydrostatic pressure restricts the vapor rising through the liquid. If overloading continues, more and
So what he's saying, that you can see that this is the internal structure of your distillation column. So there are like bubble caps. But what he is saying, that if the feed rate is increased significantly high, what will happen? The liquid will start to hold up in this trace. So like your vapor is actually flowing through the liquid, it's actually bubbling through the liquid. But if you increase this particular like depth of, or let's say the height of this hold up area, so your vapor will no longer be able to properly pass through this column, and then your proper vapor liquid like interaction will not going to take place.
more liquid backs up, and the rising vapor becomes severely blocked. This condition is known as flooding. While excessive liquid flow from a higher than normal feed rate is one cause of flooding, there are other causes. For example, a higher than normal reflux rate can have the same basic effect. Reflux is condensed overhead product that's pumped back to the top of a column. If there's too much reflux, the level of liquid on the trays can rise, increasing the hydrostatic pressure of the liquid and restricting or blocking the rising vapor. A column can also overload or flood if the temperature of the reflux is too low. A very low reflux temperature can cause too much vapor to condense in the column, which can overload the trays and impede the rising vapor. Excessive liquid flow down a column can cause overloading and flooding, but trays can also become overloaded because of excessive vapor flow up the column.
So you can see he's saying that this vapor liquid interaction, or let's say the vapor flow within the distillation column actually have multiple effects. For example, if you increase the feed rate, so that way what you are doing, you are putting more and more liquid onto this tray column, so liquid is going to hold up within your system, and your vapor transfer within vapor transport within the system is not going to take place. Let's say I have mentioned that to a certain extent increasing the let's say reflux rate is going to improve the vapor liquid interaction, but if you increase it to let's say uncontrollably, what will happen? There is going to be significant amount of hold up on the top tray. So like from the top tray, the liquid will come from this downcomer section. On the right hand side, you can see that that channel type of thing is there. That part is known as the downcomer. So from a downcomer, from the top tray, it will come down at the bottom tray. So like this type of liquid holdup is also going to take place. Another chance is that if you increase the, like let's say reduce the temperature of your distillation column to a very low temperature, what can happen? That time your condensation, like vapor condensation, can take place. If the vapor condensation take place, that may also increase the liquid holdup. And the other reason is that if you increase the, let's say if you just abruptly increase the vapor flow within the system by heating it up to a significantly high temperature, and let's say your vapor flow increases like anything, that can also lead to similar type of flooding condition. So further it has been explained here.
One of the most common causes of excessive vapor flow is too high a temperature in the bottom of the column.
Bottom
If
of
the
the column means the reboiler section. If you are increasing the temperature too high, so it is going to generate more and more vapors.
temperature in the bottom of the column is too high, too much liquid is vaporized, and the vapor flow rate up the column increases. The increased vapor flow forces liquid up the column, flooding trays in an upward progression. If the problem continues, the pressure of the impeded vapor can increase to a point where it forces liquid out of the top of the column. This condition is sometimes called puking. When the vapor
Like puking is like vomiting only. So like you are increasing so much of vapor pressure, like vapor within the system, that liquid is like kept, like liquid will be forced away through this vapor flow within the system, and it will go to the reflux drum at the top. So this phenomena is known as the puking. So but this is the, like the final example. So like initially what will happen, entrainment will happen. Like if the vapor flow is let's say slightly higher, so like little bit of what should I call it, little bit of uh, uh, like a little bit of liquid holdup will start to take place. Let's say if you increase it further from a downcomer section, what can happen, like downcomer section may actually overflow, and like from top tray liquid can come to the bottom tray, and it's the extreme condition can happen in case of this particular case, where like vapor flow is so high that the liquid is totally carried away using that vapor to the top part of your distillation column, where you will have condenser reflux drum. So like it will be directly sent to the reflux drum. So that is also one of the reasons. So like you have understood, like this type of flooding condition can happen under how many circumstances: feed rate goes too high, temperature goes too low, reflux rate you are increasing like uncontrollably, like without thinking about the internal design, and then if you increase the reboiler temperature to significantly high temperature, then also similar type of phenomena can take place. So see that how many factors actually can affect the performance of your distillation column.
pressure is relieved, liquid flows back down the column, and the pressure buildup begins again. The surging of liquid up and down a column can sometimes damage internal structures of the column. Besides the causes we've described, overloading and flooding can also occur when vapor and liquid flows become restricted by scale buildup or damage to bubble caps or packing.
So what they are saying, that since like this is one of the example that I have mentioned in the previous lecture, that why we are removing salt from my crude oil. So obviously you people might have answered in this test also that fouling can happen. So what is fouling? Like salts is going to deposit on this bubble cap tray. So like if the salt is deposited, so what can happen? So if the salt is deposited, then this vapor flow area is going to get shortened out. So under that circumstances also, where this vapor liquid flow area is going to be blocked because of this like impurities deposition, similar type of phenomena can also happen at that time.
But regardless of the cause, operators must be able to identify the problem so that it can be eliminated. A number of indicators can be used to identify overloading or flooding, including column pressures and temperatures. The buildup of liquid can cause the pressure below the flooding point to rise. So the differential pressure across the column will increase. Also, since heat from the reboiler is basically blocked from rising, the temperature at the bottom of the column may increase as well. As a result, there may be a greater differential temperature across the column. Now, if puking develops, the surge of liquid and vapor up and down the column can cause fluctuations in the pressures and temperatures, as well as in the level of liquid in the bottom of the column. Also, liquid that's forced out of the top of the column can cause a sudden rise in the level in the receiver. Now, some of the more common methods used to eliminate a flooding problem involve temporarily decreasing the feed rate, the reflux rate, or both to reduce the amount of liquid in the column, and decreasing the bottom temperature to reduce the flow rate of vapor up the column. In extreme cases, it may even be necessary to shut down the column so that the problem can be corrected.
For example, if you have in your distillation column that because of this salt deposition or some other impurity deposition, that entire column, like the flow area of vapor liquid is not that much, then what you have to do, you have to entirely close this distillation column. Other than if you're reducing your feed rate doesn't work out, reducing your reflux rate doesn't work out, reducing your reboiler temperature doesn't work out, then you have to entirely shut down the distillation column, clean it properly, check that whether this these bubble caps are like clogged with this type of fouling or not, and then you have to again clean it up, and then you can restart your distillation column.
Sir,
Yeah, tell me.
sir, sir, they mentioned reducing the reflex rate, right?
Yeah.
So which means which should be reduced, sir? The amount sent out of the column for
No, 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 no.
reflex?
Reflux is the recycle rate. Reflux
Yeah.
you understand as the recycle. So I'll just go back. The slide that I have showed you. So
Yes,
just
sir.
yeah,
So
tell me.
so when we reduce the reflex rate, which means we
Yeah.
are reducing the amount coming back inside, right? So when
No, no,
when
no,
we
no, 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 no. Actually, reflux rate is what? Whatever the lighter products that is reeving out of the system at the top.
yes,
Okay.
sir.
So
Yes, sir.
you are condensing it, and a part of the liquid you are like resending it back. So if
Yes, sir.
the reflux rate is like, if you sending back too much of liquid, what will happen? There is going to be a liquid hold up on those distillation column trays, isn't it? So because
Yes,
of
sir.
that distillation like liquid hold up, only one of the reasons was that only, like if you are increasing too much of liquid within the system, because the when this over pressure is taking place, because either your feed rate is let's say very high, or else your reflux rate is very high, where there is a chance of this over pressure, then flooding will happen, then puking can take place. So like this type of thing. So
Sir, but
so
then when you reduce the reflex rate, there would be hold up in the receiver, no, sir?
no, no, not
Because
hold up. Then what will happen? You will extract more distillate. So I'll just tell you that. For example, there is a valve. Let me just close this one and get back to the image. Okay, just a minute. Here itself, I guess that should be available. So you see here in this part. Okay, actually this will confuse you a little bit. Just a minute. Let me just close this and get back to the actual slide. Just a minute. Can you see the slide now?
no, sir. Oh, yes, sir. Yes, sir.
Yeah. You see, this is their condenser portion. So under this puking condition, so in excessive vapor flow, all the liquids going to the condenser and then coming to this reflux drum. So like reflux drum, liquid level is going to increase. No problem. So you are saying that if I reduce this reflux, this valve, if I close this valve, reduce the reflux rate, what will happen? There is going to be increased hold up in this reflux drum. That was your question, right?
Yes, sir. Yes, sir.
Yeah,
Exactly.
then what I'll do, instead of resending it back, I will open this distillate valve even more. So like more distillate will be produced. Instead of sending it back, I will produce more distillate. Like this is a product, this is one of the product that is actually, let's say you consider it that LPG is coming out. So like instead of recycling it back, I'm actually producing more LPG. Like distillate valve is going to be opened. If I close this valve, then this valve has to be opened, then only I'd be able to maintain the liquid hold up in my reflux drum, isn't it?
Yes, sir. Yes, sir.
Yeah, that is what I wanted to say. That you understand now.
Yes,
if
sir.
i if I close this, I have to open this. So or else like there is going to be differential pressure, like it's going to too much of liquid hold up can take place. Then you have to open this distillate valve and let more and more distillate production. Okay, understood. Let me just go back to the slide. Was this video was helpful in understanding how this is happening? Like is it like through the video, is it more easier for you people to understand the how this distillation column is operating? Or is like then in the like upcoming classes also I'll try to incorporate some videos within my teaching itself.
Sir, what happens exactly in puking actually?
Puking, what happens is that let's say if the I have already shown you in that, you see that in this you can consider this dashed line as a tray. You consider that dash line as a tray, and on the top of which you will have some amount of liquid which is going to remain at the top of this tray. So tray is actually holding a little bit of liquid, but if the liquid holdup goes too high, what can happen? And if you increase your reboiler temperature, or let's say in case of if you increase the reboiler temperature, too much of vapor is going to be generated within your distillation column, and it is going to pass through like this, and whatever liquid that is present in your trays is going to be carried over, because there are like significantly high vapor flow. So vapors are going to carry forward your liquids that is present on the top part of your distillation column to the directly to the condenser. You don't want condenser to deal with your actually to deal with your liquid. You want actually condenser to deal with your vapor. So puking will only happen if the vapor flow is exceedingly high. All the liquids that is present in your tray, because of this high vapor flow, is going to be carried over, and through this line it will come to the condenser, and then it will obviously get stored in this like reflux drum. So like your product quality, your operation, so everything is going to be detrimentally affected. So puking, you understand, like vomiting. So in case of vomiting, what happens? Like in case of excess gas, like it is wants to come out of your stomach. So then the same thing, puking also, puking in this distillation column is also same thing. If you have too much of vapor flow, whatever that is inside your system, inside your distillation column wants to come out. So only one way to come out of the distillation column, and that is from the top, and that is where it is actually coming out. So that phenomena will only take place under very high vapor pressure, like vapor flow, not vapor pressure, vapor flow within the distillation column. I hope that part is understood. Okay, so let me go back to the slide, because like we are talking too much about puking, the other side of the story is also needs to be understood. So like if I ask the question that under what circumstances flooding can take place, like liquid hold up on this, like increased liquid hold up on the internals of your like trays of your distillation column. So can anybody just list me out what are the condition under which this flooding condition, not puking but flooding? Can anybody tell me?
Yes, sir. So
Yes,
if,
sir.
if the feed rate is increased,
Yeah.
the reflux rate is decreased.
No, 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 not
So
reflux rate.
increased,
No,
and
yeah, yeah,
uncontrollably increased.
yeah, yeah.
And if the temperature is reduced,
Then what will happen? Then
uh,
more condensation will
more
take place. If more
condensation.
condensation take place, then also my liquid holdup is increasing. The fourth point,
The fourth point was, sir, if the vapor flow is increased,
by what? How I am increasing the vapor
due to
flow?
increased temperature in the reboiler.
Yes, we are increasing the temperature at the reboiler. And last but not the least, the fifth point.
Sir, due to deposition of impurities.
Yeah, due to deposition of impurities,
The
liquid
liquid
vapor
vapor area
flow
is
area is
increased.
actually getting reduced, and because of that also similar type of flooding condition can take place. Okay, good. At least some of you have understood. Just a moment, a
So
minute.
just one question, sir.
Yeah, yeah, sure.
Sir, in that slide, like everything which goes to the condenser is condensed, or like
Like actually
partially.
in this, like everything that goes into the condenser has to be condensed. It has to be condensed. Then only this the bottom part is the liquid. The upper part is like condenser. What does condenser do? You take
Yes.
any normal condenser also. Condenser converts your vapor into liquid only, right? That's the objective of your condenser. So like that is how it is going to be stored in your reflux drum, and from a part of your this liquid you can send it back to the distillation column. The other part you can take it out as a distillate. Just a
Okay,
moment.
sir.
Just so let's say I don't know whether this entire thing can be completed today or not, but let me just go further forward with this video. So under this, other than this puking, it can also happen that vapor flow within your distillation column can also reduce significantly. And under that circumstances, since you see that your distillation column trays are basically perforated, on this perforated tray there will be some caps will be present, so through that cap only your vapor actually rises through the column. But if your, let's say your vapor flow within the system is very low, so under that circumstances what can happen, your trays will no longer be able to hold on to that amount of liquid, and through the perforated plates your like top tray liquid is going to come down to the bottom tray, and product quality is going to further deteriorate. So the initiation of this like reducing vapor flow, this type of phenomena is happening, we'll call it as the whipping phenomena, like when a person cries, like how a tears fall, so like weeping phenomena. And then if there is no vapor flow within the system, like your system is like almost like very limited vapor flow, so under that circumstances what can happen, all the liquid that is present at the top of your column, like whatever trays, whatever number of trays will come and crashing down at the bottom of the distillation column. So that phenomena is known as the dumping. So this is the other way around. Excessive vapor flow can lead to puking, like no vapor flow can lead to dumping. Okay, so let me just restart this slide, this video.
And temperatures, as well as in the level of liquid in the bottom of the column. Also, liquid that's forced out of the top of the column can cause a sudden rise in the level in the receiver. Now, some of the more common methods used to eliminate a flooding problem involve temporarily a distillation column is too high, overloading and flooding can occur. But the performance of a distillation system can also suffer if the feed rate is too low. For example, if the feed rate to the column in this system decreases, the level of condensed overhead vapor in the receiver and the level of liquid in the bottom of the column will start to drop.
Yes.
As a result, less liquid will be available for reflux and for circulating through the reboiler. If the levels continue to fall, control devices will reduce the takeoff of overhead product and bottoms product. To correct a low feed rate problem, the cause of the problem has to be identified. If a feed line blockage is detected, it must be cleaned out so that the feed rate can be restored to normal. If an instrument reading seems unusual, it should be reported. In the meantime, the feed rate may have to be controlled manually. In addition to feed rate problems, feed temperature problems can also affect some distillation systems. For example, the temperature of the feed entering this column should be close to the temperature at the feed tray.
So like I have given one example that like overfeeding the distillation column can be detrimental. Obviously if you underfeed it also, then like liquid holdup is going to be like negligible. So if the liquid present in the tray is negligible, so like obviously the vapor flow within the system is going to come down, so that is also a very bad thing.
If the temperature of the feed is much higher or lower than the temperature at the feed tray, product separation will be disturbed. Problems can also occur if the feed mixture is contaminated with water or other foreign material. Depending on the temperatures in the column, water could vaporize and contaminate the overhead product, or settle to the bottom of the column and contaminate the bottom's product. Many of the problems that affect a distillation system can occur during startup. For that reason, operators should be on the lookout for problems such as improper feed rates and temperatures, instrument failures, and residue buildup in feed and product lines. In vacuum distillation systems, operators should also watch for leaks. A vacuum leak will cause changes in the temperatures and pressures in the column, which can reduce the efficiency of the system or stop the distillation process altogether. The feed rate is the rate at which feed mixture is pumped to a column. The flow of feed to a column can affect the quantity and quality of overhead product and bottoms product. For that reason, an optimum feed rate is normally determined mathematically based on system equipment and the materials being processed. If a system's feed rate is too high, overloading can occur. Overloading is a condition in which the vapor in the receiver liquid. In this system, the condensed liquid collects in a tank called a receiver. During startup, all of the condensed liquid is pumped back to the top of the column as reflux. The remainder is routed to overhead, is known as the reflux ratio. For example, if 4 times as much liquid is returned to the column as is sent to overhead storage, the reflux ratio.
So I guess I'm already like over with this time. So one thing you will do, like this is a 19 minutes video. I would suggest you, it's a such a very good video on understanding the operation of the distillation column. I would suggest you to go through it. So other than this, there's another video by this group only on distillation tower, reboilers and condensers. So this is around 20 minutes video. I would suggest you all the students to go through this video so that you would be able to understand like what are the consideration you have to make while operating a distillation column. And since like I have already talked about dumping, weeping, flooding, entrainment as well as puking, so this type of problem, like this type of question, definitely I can ask in the question paper. And if you just go through this video itself, the concept will be much more clearer to you, so that you won't face too much of a problem in the final examination to answer it. So let's say with this, let me just conclude today's class. I hope that it was of like, because like monotonous, I am just reading through it, it does not have that much of an interaction. So that's why I wanted to put some video into this class. So with this, I conclude today. You just go and answer the poll question. And can anybody raise hands, like those who are not being able to poll regularly, because some of the students are actually after the class contacting me that they are not being able to do so. So like I would suggest you to like tell their name. Kindly raise your hand so that I get to understand that you people have some issues in terms of like attending the poll questions, because I am repeatedly I am like marking them absent, because only basis of the poll only I am going to give you attendance, because